Thank you very much for the kind introduction and for having me. As you mentioned, I'll be talking about partial success in closing the gap between human and machine vision. And in terms of motivation, when it comes to human perception, one aspect that really stands out is our ability to recognize objects despite substantial variation. You can probably recognize the bird in every single one of those images, even though they are extremely different in pixel space. And this ability to robustly recognize objects that the human visual system possesses is something that hasn't been quite matched by a standard neural networks, standard convolutional neural networks trained on standard data sets like ImageNet. When it comes to standard CNNs and human object recognition, there's a big gaps. We know that standard CNNs make more errors on distorted images like the ones that I just showed you. Also, they don't really make human-like errors, which means that even though the task becomes much harder when they're exposed to distorted images, that they obviously make more errors. But even the errors that they do make, they aren't particularly human-like, which means that they find some images easy that humans find hard, and they find some images very hard that humans find very easy. So the question that we set out to answer or to look into is whether there's any direction in which this gap might be narrowed between standard CNNs, human object recognition. And in terms of methods, we decided to test human robustness first with a paradigm in a human psychophysical lab. So the idea is that human observers were briefly exposed to potentially distorted images like this blurred bird here for 200 milliseconds. And this was followed up by a 1/f noise mask, which is a technical detail to limit the influence of recurrent processing, since we're going to compare against feed-forward convolutional neural networks. And then humans had to pick the correct category on this response screen of 16 categories. So in this case, if humans recognize the bird, they would click on the bird. If in the next trial, if they recognize the elephant, they would click on elephant. And if they wouldn't know, they would have to guess. You can see those 16 categories. Usually, standard convolutional neural networks, they're trained in datasets like ImageNet, which has 1,000 categories. But obviously, the response screen would be completely filled up with 1,000 icons. So this is not really a feasible paradigm when it comes to testing human observers. This is why we simplified the task a bit and said, okay, 16 categories is something that's very manageable for humans. And now, since we later on want to compare machine decisions on exactly the same images to human decisions, we simply map those 1,000 categories, 1,000 categories to those 16 categories here using the wordnet hierarchy for convolutional neural networks. For example, if the response of a convolutional neural network was, I don't know, a specific type of airplane, would be counted as airplane here. If the response was German Shepherd, response would be counted towards dog here. So that way we can compare human and machine decisions on exactly the same images. So this is our human paradigm for measuring out of distribution robustness. Out of distribution because images like this blurry elephant here, or a noisy cat, or the silhouette of a car, those are images that are more challenging than the standard images that are contained in ImageNet and that are in the training set for neural networks. All right, so this is the human paradigm. When it comes to quantifying the out of distribution robustness gap between CNNs and humans, we started by testing lots of observers on lots of out of distribution data sets. And these data sets that we tested were contained both parametric transformations, for example, different degrees of rotation or increasing amounts of noise applied to images, and also non-parametric transformations like silhouettes or line drawings. We picked those 17 because we intended to cover really a broad variety of this different out-of-distribution challenging test cases. And then on the machine side, we tested 52 different models. And in addition to standard CNNs, for which it's fairly well known that there's a robustness gap, we decided to look into 3 promising, interesting directions. The first direction is models that deviate from standard CNNs in the sense that they have a different objective function. For example, self-supervised models are really interesting because they cope without human-provided labels. Also, adversarially trained models are much more robust towards adversarial type distortions, and CLIP is jointly trained on image and text, which is also a very radical difference compared to standard CNNs. So that's different objective function. We also tested models with a very different architecture, like vision transformers, which are becoming the dominant paradigm in computer vision. And we tested models that were trained on a variety of dataset sizes, so ranging from 1 million images like standard imaging all the way to 1 billion images to see whether the training dataset size has a crucial effect as opposed to or compared to standard CNNs trained on standard imaging. All this is now brought together in a single comprehensive toolbox and benchmark that we put available on GitHub, so that it's hopefully a useful resource if people are interested in testing their own models against human psychophysical data, against human robustness data. Before we look at the results, I would like to briefly mention why I think it's very important to compare human and machine behavior specifically. Behavior means essentially looking at the input-output relationship. So given the same input, do a human observer and the machine produce the same output, the same prediction? And I think there's a number of reasons for why this might be promising. The first aspect is really comparing behavior, input-output relationships has direct practical relevance. If we think of internal representations, those are sort of machine thoughts, something that happens in between. But in the end, in application settings, the most direct practical relevance is really the output decision. And this is something that influences people when they're faced with a machine decision. So it's really the decision that counts in practical settings rather than something that happens in between, even though the intermediate steps obviously constrain and inform the decision usually. But the highest direct practical relevance is in the decision itself. Furthermore, I'd say it's becoming better, but still behavior is rather understudied compared to representational analyses like RSA and variance. It's also analyzing behavior is non-invasive when it comes to humans, and there's no retraining required when it comes to machines, which allows for a fair comparison that doesn't come with the ethical challenges of invasive methods and all the design choices that come with retraining, for example. Furthermore, analyzing behavior allows to transfer psychophysical methods, established psychophysical methods. Psychophysics is a small field within psychology that usually or historically had the intention of bringing the rigor of physics to the study of humans, of psychology. And we can now take this, the methods from this well-established field and try again to bring this scientific rigor to the analysis of machine learning models. because psychophysics has a long history of understanding black box perceptual systems such as our visual perception. And that makes it an excellent toolkit to use. And last but not least, behavior aims at the algorithmic functional level of comparison, which sort of the input-output relationship, the computation. And in contrast, for example, the implementational level is a very challenging one. I think if we wanted to build a neural network that exactly captures all of the details of the computations that are going on in the brain, including, you know, synapses and neurotransmitters and everything, I mean, it would be great if we had that, but even if we managed to replicate a brain in silico, the question is, well, would we have understood anything, or would we have rather end up with a map that is essentially the size of the world? So in this sense, looking at computation rather than implementation, I think makes sense, and this is what we aim to do with this behavioral analysis. All right, this was a bit of a detour, kind of a motivation for why I think it's important to compare human-machine behavior. Although other aspects are, like other methods of comparison are also obviously very, very valid and interesting. As a disclaimer, before we dive into the results, I should mention that robustness is a very broad term, and robustness is studied from many different viewpoints. There's adversarial robustness, there's robustness against various transformations. There's lots of different angles to this question. Here we specifically focus on out-of-distribution distortion robustness. Furthermore, humans and machines can and should be compared in many different ways. We just focus on robust visual object recognition here. And I've mentioned this before, it's a functional, it's a behavioral approach, which is opposed to comparing internal representations. So even if we find, for example, dissimilarities at the output level, this doesn't mean that there's also dissimilarities at an intermediate stage. That's a different question. We here focus on the function, on the behavior. All right. So in terms of results, we started with the question of, well, we knew that standard CNNs make more errors on distorted images, and they don't really make human-like errors. So we start with the question, well, how do more recent models perform? Models that crucially deviate from standard CNNs in a number of ways. And we're going to look at two different aspects here. The first aspect is, well, simply how many errors are those more recent, potentially exciting models making? How many errors? That's measured by accuracy. And then the second part is going to be about whether the errors that they make are human-like, or the same errors that humans make. And that's measured by error consistency. Starting with the first question of how many errors, we can look at object classification accuracies as a function of the amount of noise that is applied to an image. For example, here in this image of a biker, you can probably recognize the first 5, maybe 6 images from the left, but it becomes close to impossible to recognizing the biker when there's like substantial levels of noise. And we can show lots of these noisy images to humans and to neural networks and record how the classification accuracy drops when the task becomes more challenging and harder. And this is exactly what is plotted here. We can see that human observers sort of gracefully decline in their accuracies when the noise strength increases, whereas standard CNNs, all of those are essentially the torch vision model zoo models. All of those in gray drop rapidly as soon as a bit of noise is applied. And well, you might be asking yourself, well, why don't we simply include distortion in the training data? So, for example, if if we're faced with uniform noise, let's just train models on uniform noise and we're good to go. And I'll try to convince you that this might not be a general solution. Why not? Well, if we train on uniform noise and we test on uniform noise, you're absolutely right. Performance is going to be superhuman, in this case, 80%. If we, however, train on uniform noise and test on a slightly different type of noise, salt and pepper noise, which to you looks hardly distinguishable. So you can probably see some bright and dark patterns here. Salt and pepper noise essentially means switching pixels to either black or white. But it's very similar. If we just train on uniform noise, test on salt and pepper noise, the performance of this model drops to chance level. So that's clearly a concern. And well, the next question is obviously, okay, maybe we don't just train on a single type of noise, but test on multiple ones. And this is exactly what we tested here. So you can see different distortions here in different rows. And you can see that on the diagonal, that's essentially the distortion that the model was trained on. So we have one model just trained on color images, one model just trained on grayscale, and then it's tested against all the other distortions. One model is just trained on contrast, and it's tested against the others. One is trained on low pass, tested against all the other distortions. And we can see that between color and grayscale, there's transfer, there's generalization. So the model trained on color does well on grayscale. The model trained on grayscale images does well on color. However, for all the other cases, pretty much the performance is close to chance level of 6%. And this pattern doesn't disappear if we include two distortion types. So if we train a model on color and uniform noise, it does very well on color and uniform noise, but poorly on all the other distortions. If you train a model on salt and pepper and uniform noise, it does very well on salt and pepper and uniform noise. It does poorly on all the other distortions. And in the extreme case, we can even test training on all except for a single distortion, and then testing on the single distortion. And again, the model does very well on all the distortion types included in the training data, but it shows close to chance level accuracies on the left out distortion type. So with that in mind, I think it's fair to say that simply including distortions in the training data only works if we know exactly in advance which distortion type we're going to encounter at test time. However, this assumption is quite unrealistic when we think towards building machines that work in the real world, where it's not always clear what type of distortion we're going to encounter, and that's why we need better methods, better models that generalize, even though they haven't been exactly trained on the specific types of noise. So coming back to the question of uniform noise, how many errors models make? Is there any direction which is going to narrow this gap between standard CNNs and human observers? Unfortunately, the answer is yes, actually. There is a family of models that narrows this gap. As you can see here, all those colorful models, they radically improve over standard CNNs. Trained on ImageNet, 1 million images. And those models are simply standard CNNs, the same standard architectures, but they're trained on 10 times, 100 times, or even 1,000 times more data compared to standard ImageNet. So simply increasing the size of the training dataset by orders of magnitude seems to be a key ingredient in obtaining human-level robustness on uniform noise, which is the example here. So the question is, obviously, is this just a finding that's limited to uniform noise, or is this a more general finding? What about the other 17 data sets that we included in the toolbox. So this is a very crowded slide. Apologies for that. We don't need to go into details here, but as you can see, human observers in red are being surpassed by the best models in nearly every single case, except perhaps for low-pass images. So models are becoming much better at generalization against various types of distortions, and we can quantify this by just looking at the average out of distribution accuracy of humans and of models in comparison. So across all of those 17 data sets, average human out of distribution robustness is at a fairly high level, and as we know, there's a pretty substantial gap between humans and standard CNNs. Fortunately, however, this gap is closed, not just narrowed, but essentially closed by data-rich models trained on larger data sets. And all of those models with a red arrow on top, those are models that are trained on larger data sets, as opposed to standard ImageNet. And data set size thus seems to be much more important than other aspects. For example, standard CNNs are displayed in gray here, and the gap isn't closed by self-supervised models in yellow. And it's not claimed, the gap isn't narrowed by adversarially trained models in blue either. It's really the data set size that makes a crucial difference here.
So can I ask a question about
this? Please.
So since we're really making the data sets larger, is it possible that we are implicitly making the out of distribution task more in distribution, because we have so many more data here? Like maybe some of them might have similar distortions as the target distortion.
Yeah, that's a great question. And I think when it comes to those giant data sets, like Noisy Student is trained on 300 million images. There's other models trained on a billion images like SVSL. Usually those data sets are proprietary. So they're being developed by companies like Google, OpenAI, Facebook, and so on. And the data sets aren't usually released, which means that it's becoming harder and harder to actually tell what is in distribution and what is out of distribution for those models. I think for the purpose of those results here, it's important to look at every single distortion type. There's some distortion types like blurry images, for example, or grayscale images that are quite likely to occur on web-scraped large data sets. So in this case, I think it's fair to assume that there's a certain portion of those data sets that are becoming more and more in distribution. At the same time, we included some distortions in our test case, like eidolon distortions that are specifically designed for research purposes, and they're fairly recent, and there's no, like, you can't really find images of eidolon type distortions on the web. Maybe if I go back a few slides on the bottom row, you can see the eidolon distortions. And what is reassuring is that the best models are also getting better on those clearly out of distribution data sets. So there seems to be something more general that happens. Even though, yeah, absolutely, it becomes harder to distinguish between in distribution and out of distribution if you don't have access to the data set.
I see. Very interesting. Thank you.
Great question. Thanks. All right. So this was the first aspect. The first question. We've seen that standard CNNs have a big gap in terms of robustness compared to humans. but data-rich models are closing this gap. The next and the second question that we looked at is whether models and humans make similar errors and whether there's any trend here that we can see. So this is measured by error consistency, and I'll try to give you an intuition for how this metric works. Error consistency is based on Cohen's kappa, which is usually or traditionally used to measure inter-rater agreement in psychology. But we can use that for the analysis of machine learning and human errors. So let's pretend you're walking to the lab and you're asked to classify those images, just as we asked our participants. So one after another, there's going to be images, and you have to classify those. And you're probably going to get some of those right, like the airplane and the chair and so on. And you'll probably also make errors on other images. And the same is true for a machine. And once we have this vector of decisions, we can compare them on a image by image level, and not just look at aggregate measures like accuracy that sort of lump all of those images together, but we can look at every single case and count, well, how much overlap do we get? And in this case, that's an extreme case, we get perfect overlap between correct decisions and wrong decisions. So if both the human and the machine make the same decision at every single trial, we would get perfect agreement, and error consistency would take a value of 1.0. Another example is, well, we get some wrong, some right, and a machine also gets some right, some wrong. But in this case, there's no consistency whatsoever. In fact, there's systematic disagreement. So in this case, error consistency would take a value of negative 1. And usually it's probably going to be somewhere in between. And in this case, there's a certain overlap, but not a perfect overlap, 3 out of 6. In this case, this is exactly the overlap that we would expect by chance alone, which is a very relevant baseline. How much overlap are we going to get? Even if the human and the machine decision are completely independent. So in this case, error consistency would be 0, which means there's only chance level agreement. And as soon as there's beyond chance level agreement, we have positive values for error consistency. If there's below chance agreement or systematic disagreement, error consistency would be negative. So we can look at error consistency between humans and machines. And again, 0 means completely independent errors. Positive values means making errors on the same images. And human-to-human consistency is at a really high level. So images that one observer finds difficult are also the images that another observer would make an error on. And there's this high level of consistency, sort of the highest that we can hope for when it comes to comparing machine versus human decisions. However, there's a very substantial gap again between standard CNN and human level consistency. It's not 0, which means there's a certain degree of agreement between humans and machines in terms of which images they find easy and difficult, but it's far from perfect. There's a big consistency gap here. And again, there's progress through more recent models, the more colorful models here. All of those models with a red arrow on top are again the models that are trained on large scale data sets, which again seems to be important in narrowing the consistency gap towards human level consistency. And the clip here in brown on the very right really seems to be standing out. The most human-like model, even though there's still a substantial gap that is remaining here. So again, a very simple trick, essentially training standard models on larger data sets seems to go a long way, even though models like CLIP, which also have a different objective function, they're trained on both images and text, and a different architecture, like vision transformers, that gives another boost in performance, even though, yeah, it would be great to disentangle those components and really figure out whether all of those different changes have to occur at the same time, or whether it's maybe just a single or maybe two of those components that make CLIP stand out here. So yeah, there's still a gap between machine and human consistency, but that gap is narrowed. So far, we've only looked at consistency between machines and humans. Obviously, a natural question is to ask whether how the consistency between different models looks like. And this is exactly what we can see here. So here's the matrix of consistencies. So comparing AlexNet to itself, it's obviously perfect consistency. So the diagonal is at a value of 1.0. And then the off-diagonal values are comparing, for example, AlexNet against all of the other standard supervised CNNs. And we can see that there's a very high degree of consistency between different models. So even though AlexNet and, for example, MobileNet or ResNet have very different architectures within the common framework of CNNs, the consistency is really high, remarkably high. I was quite surprised when I saw this for the first time. And what's more surprising here is that even the consistency between standard CNNs and very different models is extremely high. So also when we look at self-supervised models, trained in a radically different way without human-provided labels, consistency is high. Consistency to adversarially trained networks in blue is high, and the consistency even to vision transformers is very high. In contrast, the consistency between models and human observers is fairly low, as you can see here. And again, obviously, the consistency within human observers is again like a cluster here. And as we've seen in the previous slide, CLIP really made a huge step towards human-level robustness. And in this case, you can see here that the consistency with human observers is at a fairly high level when it comes to CLIP, the lowest row here. And remarkably, the consistency between CLIP and standard models is going down. So it's really more human-like in terms of the errors that it makes, and it's less machine-like when it comes to those standard models. And we can also look at some other models, which again mostly cluster sort of in the big machine in the machine cluster here. So it's not perfect agreement here with humans. Mostly those data-rich models also make errors that other data-rich models would make. Not exactly the errors that humans would make, but it's better than standard supervised CNNs. The last aspect that we looked at was really, well, we've seen accuracy, how many errors do humans and models make, and we've seen error consistency. Are the errors that models and humans make the same errors? They find the same individual images easy and difficult. And really, the last question that we looked at is the combination of those. Is there any trend when it comes to plotting accuracy versus consistency? And the finding that we had here was kind of twofold. There's two different variants. So we split the data by human accuracy, whether human accuracy is lower than the best model's accuracy, or whether human accuracy is larger than the best model's accuracy. And when it comes to data sets where models are better than humans, or at least the best models are better than humans, we can see that error consistency sort of hovers around this value of 0.2. Error and out of distribution accuracy on the x-axis sort of spans a wide range, but there's no trend that is getting closer towards human level consistency here. So that's why we call those maybe the kind of disappointing data sets, even though we don't really understand why those data sets are not others. Looking at the data sets where human observers were better than the best model, we get a completely different trend. Here it's also almost a perfect regression line pointing towards human level robustness, and you can imagine that getting slightly better models in terms of out of distribution accuracy might just close the consistency gap towards human observers when it comes to those promising data sets. So really a twofold finding here. On one side, humans are kind of off the chart when it comes to consistency between models and humans. A big gap, and it doesn't really matter whether a model has high out of distribution accuracy or low out of distribution accuracy. And on the other hand, we've got this almost perfect regression fit, where humans are sort of pretty much on the same line as models, just a bit better in terms of distribution accuracy and a bit higher in terms of error consistency, but definitely sort of along the trajectory of models that we can see. And it's, yeah, the trajectory is surely going to close or reach humans there. You can see those gray points are standard CNNs, in orange or yellow are the self-supervised models, and then triangles are vision transformers, and those purple and pink models are standard CNNs, trained on large-scale data sets, with CLIP being in brown, perhaps the most human-like model according to those data sets. So something interesting going on here, even though we don't really quite understand why there's this big dichotomy between promising and maybe disappointing data sets. All right. In terms of outlook, when we think about those findings, I think it's great that the long-standing out of distribution distortion robustness between humans and machines is closing. We've seen a pretty substantial gap between standard CNNs trained on standard data sets and humans for a long time. So now this gap is really closing, and in many cases, the best neural networks have surpassed human out of distribution robustness across a broad variety of data sets, of really challenging data sets. In terms of image level consistency, there's still a substantial gap. Humans make different errors than models. Humans make the same errors as other humans, models make the same errors as other models, but those two groups don't necessarily make the same errors. Again, however, in both cases, there's progress through large-scale data sets. And both robustness and image level consistency, they improve simply by increasing data set size between 1 and 3 orders of magnitude. On one side, it's simple because it doesn't require any architectural modifications or new objective functions. On the other hand, training on a large-scale data set also comes down to obviously with many challenges in terms of compute, energy, resources, and so on. So it's not as simple as we would like it to be, but it's conceptually not a very difficult thing to do, just increasing the data set size. In our interpretation, it's a bit of a bittersweet lesson. On one side, it's definitely sweet to obtain human-level distortion robustness. That's something that we definitely need in terms of real-world applications, and it's fantastic that we now have models that are pretty much getting there. And also, finally, we get improved behavioral consistency with humans. If you think back of this big matrix, when we just looked at different variants of CNNs, they were pretty much interchangeable when it comes to error consistency. So really, it didn't really matter whether we looked at AlexNet, ResNet 152, ResNet 18, MobileNet, any other model. Behavioral consistency with humans was at a very low level. Now we finally get improved behavioral consistency with humans through large-scale data sets. That's also on the sweet side. On the other side, I think it's also important to acknowledge that this is not all great. So there's also a bitter side to this. First of all, the models that show the most human-like behavior, they are engineering achievements, but they're not particularly biologically inspired. They don't have neuroscience-inspired normalization layers or neuroscience-inspired architectures. They're pretty much trained on large-scale data sets. So that's certainly something to think about, and something that maybe challenges our intuitions a bit. And large-scale data sets appear to be much more important than architectures or for example, self-supervised learning as a learning strategy, which has this clear biological motivation that humans don't require a million labels during development to learn what objects are like. So there's a clear biological motivation in terms of self-supervised learning, but behaviorally self-supervised and supervised models were pretty much interchangeable. And even though computer vision as a field spends a lot of time and effort on new architectures, in this case here, simply increasing the dataset size seemed to be the most important ingredient. So I think this is sort of the picture. There's a sweet side to this, and there's also a bitter or maybe challenging side to this. Something to think about. And with that, I'd like to thank you all for your attention. I'd also like to thank my amazing collaborators here, Candaracho, Benjamin, Tizian, Matthias, Felix, and Wieland. And I look forward to any questions you might have.